Hi everyone, I hope you're well. This is the introduction to Project 4, Synchronization. So let's start out with, excuse me, where you can find resources for the project. So there are a number of resources here under the project heading. The project description mentions some additional resources available in the textbook and also mentions the pthreads resources at the bottom of the course website on Phoenix. All right, let's look at the project description. So you're going to work on variations of two of the classic synchronization problems, Tiny Philosophers and the Sleeping Barber. You'll be creating a threads-based solution using the pthreads library. And as you can see, mutex and condition variables in Tiny Philosophers and POSIX unnamed Semaphores in the Sleeping Barber. Okay, you can do your work on Phoenix. You can also do it on your virtual machines, although you may have to use apt to possibly download some of the pthread stuff. I haven't tested any of this on the virtual machines. So here's a refresher on how to create a new project. So in Canvas, you're going to use this link to create a new repository for your work. And the URL for that repository you'll be plugging in here, where it says your GitHub repo URL. Right, so create a new directory for the project files, cd into it, init it, add the remote, add files. So in this case you'll have two, diningphilosopher.c and sleepingbarber.c. Add them, do your initial commit, and the first time you do a push, use this form, and then for all of your subsequent pushes, use this form. Okay, remember the sequence. So remember, you should push early and often, run git status to check to find out what files have been modified, use git add to add those files, then do the git commit and a git push. Okay, if you haven't used git on Phoenix, run these commands to configure your git tooling. And those. Okay, so here are the the references that were mentioned. I'm going to go through these, starting with these demonstration programs. Okay, and please don't add these to your repository. But you're not submitting these. What you have in your repository should just be the work that you'll be submitting. So Semaphore.c here is just a very brief illustration of how semaphores are used. So note, you can download these programs and compile and run them just to see what happens. The header file for the semaphore functions has to be included. Here's how a semaphore is declared. Notice that it's of type semtype. Semaphores have to be initialized before they're used. So note that the first parameter is a pointer to a semaphore or to a variable type semtype. Okay, you can check the documentation for seminit for what the second parameter means. For us, that should always be 0. The third parameter is the initial value of the semaphore. So for a binary semaphore that you would use for locking, you want to initialize that to 1. Counting semaphore, initialize it to something between 0 and n as appropriate. Sempost is the signal operation. Keep in mind it takes a pointer. Semwait is the wait operation, and again it takes a pointer. Okay, next program. Alright, so this is a pthreads based solution to producer consumer using mutex and condition variables. Alright, so mutexes are of type pthread mutex type. Condition variables are of type pthread cons type. Okay, so there's some defined constants. These are all global variables. These are the prototypes for these functions to make the compiler happy, because I defined producer and consumer after I defined main. The compiler main is referring to producer and consumer, so the compiler wants to know the return type and the parameter types of these functions. Okay, and note, with any function that you're going to use as the function that a thread runs, this has to be the return and type signature. It returns a pointer to void, and it takes as a parameter a pointer to void. That always has to be the case. Okay, so pthreads are implemented as variables of type pthread type. So in this example, there are 2 producers, hence pro is an array of size 2, and a single consumer. All right, first thing, initialize the mutex and the 2 condition variables. And again, you can check the documentation for what null here means for the second parameter. Okay, creating the threads. Okay, and also notice we're always passing pointers. Here we're passing pointers again. Check the documentation on why that's null. The third parameter is the name of the function that should be run, and note that it's just the name. The fourth parameter is the parameter to pass into the function that'll be run. Okay, so null, the null pointer is automatically of type pointer to void. Here I'm playing a trick. The first producer, I'm passing in the number 0. So I'm passing in it as a long. So this is actually 0L. Right, that L suffix means that the type of 0 there is long. Here it's 1L. We're casting those longs to pointers to void, and you'll see in the functions themselves they're cast back from pointer to void to long. Okay, and then I want the main thread to hang around waiting for the consumer and the producer threads to finish. So we do that with pthread join. Okay, I'll go through the producer here briefly. Okay, so pointer is the pointer to void parameter. Note that I'm casting it back to a long and storing it as the thread ID. Okay. And then this producer will produce max items. So it grabs the mutex. And then if there are no empty buffers, remember the producer needs empty buffers to produce into. If there are no empty buffers, it waits on the condition variable for producers. There are separate condition variables, for one for the producers, one for the consumer. And a condition variable is always associated with a mutex. The name condition variables, perhaps a little confusing. This is actually the condition. The condition variable is really just an object that allows a thread to wait on. And they're always associated with a mutex. Remember, at this point, the producer holds the mutex. So if it just went into a wait, holding the mutex, then the consumer wouldn't be able to consume a buffer, creating an empty buffer. So condition wait, when it waits on this condition, it simultaneously releases the mutex. And when another thread either does a signal or a broadcast, waking this thread back up, it will first reacquire the mutex before continuing. Now, in the textbook examples, you will generally see an if statement here. Always use a while, because in practice, you are not guaranteed, particularly if a broadcast is done, since that'll wake up all the waiting threads, you're not guaranteed that the condition is actually true. So always use a while to guard the condition wait. Okay, so this is just some code to do the production. Here we're signaling the consumer and releasing the mutex. And then here's the remainder section. We're just sleeping for a little bit of time. All right, so the one thing I'll mention in consumer, after the consumer consumes something, it does a broadcast, which will wake up both producers. All right, so that's just to illustrate broadcast. Okay, what was the hello threaded? This is just an example of how to manage a large number of threads. Right, and that's done by just creating an array of pthread type and working with that array when creating the threads and joining on them. Okay, let's go back to the project handout. Okay. Right, so this is the basic, view this as the basic framework for the thread functions you'll be writing. Right, so this general framework will work for your philosopher, Barber, customer, the VIP customer for sleeping Barber. Okay, so at a minimum, you want to include these header files. Here are function prototypes. So here's a delay function. It's for both problems you'll be working on. You want to put the threads to sleep from time to time. You should use this function to do that. Okay, so here's the declaration of one of the actors. And don't use names like actor 1, actor 2, actor 3. name your thread functions, things like Barber, customer, philosopher. Okay, right, so generally one of these actors will, maybe yes, maybe not, get an ID number from the main thread, use that as a seed for randomizing the sleep, and then go into, in this case, either an infinite loop or some sort of a conditioned loop, and then alternate back and forth between remainder section, critical section, where shared variables are being accessed, perhaps another non-critical section, etc. Okay, so this is a quick illustration of creating that thread and joining on it, and then also for the log messages that you'll be generating, you want to enable unbuffered output. Sometimes C will hold on to a number of printf statements, buffering them until a certain quantity of output is ready to be pushed to the monitor. You generally, when working on these sorts of problems, want to see the output immediately, so you want to unbuffer that output. Right? And these two statements at the very beginning of your main function will do that. And at the very beginning, remember, you have to declare all your variables first. Okay, for doing timestamping messages, you'll find this function very useful. And here's an example of how to use it. So you declare char array to hold the message, use sprintf to produce that message into your message buffer, and then pass that completed message to the timestamp function. Okay, so for dying philosophers, there's an example on the course website. We'll switch to that momentarily, of a solution for a monitor. So you're going to adapt that to using mutex and condition variables, which is a small twist. The larger twist is to prevent any philosopher from starving. You're going to use a turn variable to prioritize the philosophers in a circular manner. So the idea here is, if it's, let's use this example. If it's philosopher 3's turn, so turn is 3, and philosopher 3 is hungry, then philosophers 2 and 4, or the two philosophers adjacent to it, should be prevented from eating. Eventually, philosopher 3 will eat. When it's finished eating, it should increment turn in a modulo sense. And so we have 5 philosophers, right? So after philosopher 4's turn, it's philosopher 0's turn. But as this suggests, if it's philosopher 3's turn, and philosopher 3 is just thinking, it's okay for philosophers 2 or 4 to go ahead and eat. It's only if it's a particular philosopher's turn and that philosopher is hungry that its neighbors should be prevented from eating. Okay. The monitor solution uses an enum. Here's how to do that in C. An example of how to work with it in C. Okay, let's look at the pseudocode. All right, So here's the enum. Here's view this as pseudocode. So each philosopher has its own condition variable. The big advantage of a monitor is that it has an implicit mutex that is locked when any function inside the monitor is invoked. So you're going to have to make that explicit and add a mutex. The state array, these condition variables, the mutex, turn, which I would just declare as an int, are all global variables. Implement these functions separately. Right? I don't want to see you taking this code and dropping it into the philosopher function. I keep everything modular. You may have to read over this a couple of times before it starts to click with respect to what's going on. Test is a function that tests whether a particular philosopher can make the transition to eating from hungry. And you'll notice that it's called in two places. This place is obvious. If a philosopher wants to start eating, it invokes test and then checks to see if test changes its states to eating. That makes sense. Invoking it here may not make so much sense. So the motivation for this is once philosopher I stops eating and goes back to thinking, it's possible that either of the adjacent philosophers can begin eating. So as a courtesy, not so much as a courtesy, because if those philosophers couldn't eat, they're waiting on their condition variables. So rather than a courtesy, this is necessary. Philosopher I invokes test on the previous philosopher, right? In modular arithmetic, where we're doing things modulo 5, this is the way we subtract. And it runs test on the next philosopher, again modulo 5. And this is the way we add one in modular arithmetic. Okay, so in my implementation, I added a defer function that checked the turn variable. Right, for philosopher I, it checks to see whether the philosopher to the left or to the right is hungry, and its turn, right, and return 0 or 1 according to that. And then I used that in test. All right, so I recommend you do the same thing. Write a separate defer function that checks turn. Okay, so the initialization code, this is what's going to go in main along with other things. Right, you'll need to set the state of all the philosophers to thinking. You'll need to initialize the condition variables. You'll need to initialize the mutex. You'll need to create the 5 philosopher threads and then join on them. Okay, and let's see. So they run forever. So to terminate your program, you'll use Control C. That should terminate the program. Okay. And I added, I used the timestamp function to add log. You're not writing to the system log. You're just writing the standard output. but I used the timestamp function to indicate when a philosopher would change state. And I think when it was sleeping as well. So sleeping Barber, here the twist is that there's a VIP who never has to leave the barber shop because all the chairs are occupied, and is always, when the VIP comes in, the next person to get a haircut. So if a regular customer is getting a haircut, that customer is not preempted. But if there's another customer waiting, the VIP gets to get their head cut before that waiting customer. Okay, again, I used the timestamp function rather than printf here to print messages indicating what was going on. Okay, in this rendezvous, I'll point out this this additional semaphore for the rendezvous when we go through the pseudocode. Okay, pay attention to the various wait times here and the conditions under which you should do your testing. Okay, what did I say I named that additional? Okay, I'm going to refer to that semaphore as rendezvous. Okay. So here's the pseudocode. There's a customer's semaphore, the Barber semaphore. I added an additional semaphore for the VIP customer. The mutex semaphore, awaiting. This is the number of waiting customers. And also an int that I use in a Boolean sense to indicate whether or not the VIP customer was present. Okay, I modified the first part of the Barber here a little bit. I actually looked at waiting and the Barber. Oh, I grabbed the mutex. These are shared variables. You shouldn't be doing anything, either reading or writing to them without having the mutex. And then I checked to see whether the VIP was in the barber shop, were there any waiting customers, and then printed a message and went to sleep or carried on as the case was, right? And so that required me to change this code up a little bit. And then you'll have some logic here. Remember, the VIP customer has priority, right? So you'll have to structure your code to make sure that the VIP customer is serviced if it's present. Otherwise, move on to the other customers. Okay, so cut hair and get haircut are where the rendezvous semaphore come into play. Get haircut was just a wait on the rendezvous semaphore. Cut hair was signal on the rendezvous semaphore. And so in other words, we're forcing the customer to wait getting its haircut, and the barber signals when the haircut is finished. The code for the VIP customer will be quite similar to this, except instead of working with the customer's semaphore, it'll be working with the Barber semaphore, or I'm sorry, the VIP semaphore. Hold on a second. Hi, I'm back. I noticed I needed to pause because I noticed a potential point of confusion. The barber waits on customers. The customers wait on the barber. So to keep that analogy going, for the VIP customer, I would have a Barber's VIP semaphore that the VIP customer waits on. So the VIP customer will still signal the customer semaphore, but it'll wait on the Barber VIP semaphore. Okay, so hopefully that clears that up. Okay. Okay, so when you finish, you'll turn this in by emailing me the URL of your GitHub repo. And here's how you'll be assessed. I prefer short functions to single long functions. And by looking at your program's output, I should be able to clearly see that your program is meeting all the requirements. Okay, you all take care. Bye.